So we're talking today about chemical equations. And what we want to understand about chemical equations is kind of stuff we've already kind of talked about before. We know that the reactants are on the left side. We know that the products are on the right side. We know that the arrow connects the two together to kind of separate what are reactants from products. What we really haven't talked about yet, though, is we can give chemical equations a little bit more context and a little bit more depth through the use of phases. And so we will use phase or state notation a lot of times here to help us to indicate and show what kinds of phases of matter are involved in the reaction. And the phases of matter that are relevant to us are these right here. So we will use G for gases. We will use L for liquids. We will use S for solids. And the last category here, AQ, aqueous, this is an example of kind of framing what the chemical reactions are that we're really focusing on in this chapter, which are those that occur in solution. So if I have a compound dissolved in water, we know that that is a solution. We know that it's a homogeneous solution. But with water as its solvent, we can more specifically call it an aqueous solution. Aqueous being derived from aqua, water. And that's why we use AQ as its designation. So we've discussed the idea of solutions going all the way back to chapter 2 when we were classifying matter. But now we have a way to show that a solution is present in a chemical reaction, in a chemical equation. Now, when it comes to what we're talking about today, we are talking about classifying chemical reactions. And when we talk about classification, what we need to understand is that there are some groups, some things that we can do as far as classifying is concerned that help us to put things into proper groups and help us to predict what's going to happen. So this is a flow chart out of your textbook. But let's talk about each of these here in turn. So you didn't get them off of the flow chart here. We're going to talk about each of them individually now. So when we talk about chemical reactions, we usually classify them based on what's happening in the reaction itself. What is going on? Your book describes this as classifying by looking at what the atoms are doing. And what we can see in this kind of mode of thinking is that there are three kinds of things that atoms can do. They can come together. We call that synthesis or combination. They can break apart. When we see a molecule break apart into smaller pieces, that's called decomposition. Or we can see atoms switch places. When we see atoms switch places, that is known as a displacement reaction or a replacement reaction. And there are two different forms: the single displacement and the double displacement. The main difference between them is single displacement, we have one compound present in the reaction. Double displacement, we have two compounds in the reaction. So this is probably the simplest mode of classification, is just looking at, okay, what do my reactants look like versus what my products look like? And based on what I see, I can put them into one of those four slots. So I see them coming together, I know it's synthesis. I see it breaking apart, I know it's decomposition. I see things switching around, I know it's displacement. I just need to figure out which kind of displacement it is. And so I look at the actual chemical equation and I see, oh, this one just has one compound as a reactant, it's single displacement. This one has two compounds as reactants, I know it's double displacement. So going kind of deeper with each of these, synthesis or combination reactions, we see this kind of behavior. Two or more simple substances combining to make a more complex substance. In this picture example, you have sodium metal being placed in with chlorine gas. And once the reaction has had enough time to occur, we see sodium chloride table salt as the result. We started with two simple substances, two elements. They came together to form a single compound. By contrast, a decomposition reaction is effectively the opposite. A complex substance breaks apart to form simpler substances. An example of this is water. If I hook up water to an electrical source like a battery or to some other kind of provider of electrical current, the water is split apart into the elements that make it up. Hydrogen on one side, oxygen on the other. And the diagram tells us which one is hydrogen, which one is oxygen. But we also would know just from its chemical formula, there's twice as much hydrogen than there is oxygen in water. So the test tube with the larger amount of gas, we would expect to be hydrogen as a result. With single replacement or single displacement, what we see is an element displacing another element in a compound. So, easy example of this would be if I have a solution of copper 2 chloride here. We know it's copper 2 chloride, or we at least know that it's copper as an ion because copper solutions appear blue. But if we dip a strip of zinc into that copper solution, what will happen is that the copper ions will start to deposit on the zinc strip and give us copper metal. So chemically speaking, we started with zinc and copper 2 chloride. In the end, we're going to end up with copper metal and zinc chloride as a result. The zinc has kicked out the copper from the compound. So that's single displacement, yeah.
Copper no longer copper now, or is it copper?
That's no longer copper too. So we'll get into this in later examples, but this is also an example of what's called an electron transfer reaction, where in addition to the zinc kicking it out, the zinc is also giving it 2 electrons, so that the copper goes from being an ion, which would dissolve in water, to a metal, which would not dissolve in water. So in order to dissolve in water, the metal needs to be ionic. And so what we'll see is that electrons get transferred in that process of this particular type of displacement. Now, in the other type of displacement, what we see instead is we start with 2 solutions usually. And in the process of 2 solutions mixing, we end up getting some kind of insoluble product as a result. So you may not be able to see it from where you're sitting because the print's a little bit on the small side. But we have the same kind of thing going on. We have displacement taking place. The potassium and the lead are switching spots. That's how we know it's displacement. We're seeing the exchange of, in this case, ions. There are no elements here, it's all ions. So we're seeing the exchange of ions here. And as a result, we get 2 new compounds. We started with we started with potassium iodide and lead 2 nitrate. Now we have lead 2 iodide and potassium nitrate. Well, the thing is, lead 2 nitrate is this yellow solid here. Lead 2 nitrate doesn't dissolve in water. So if you want to think back to what we talked about at the very end of Wednesday's class, one of the signs of a chemical reaction, the formation of a solid. This is an example of the formation of a solid. I started with a solution where everything was dissolved. I added another solution where everything was dissolved. When I put them together, I suddenly have something that isn't dissolved anymore. The evolution or formation of that solid lets me know that a chemical reaction actually took place. This is an example of that kind of reaction. Now, that was unintentional. In these double displacement reactions, there are subcategories. These subcategories have a lot to do with what kind of result are we seeing. So what is the thing that triggers in us the response that something has happened? So in precipitation reactions, that thing that is happening is that we're seeing a solid form, like this. In acid-base reactions, we are seeing a change in pH and formation of liquid water. And so neither of those two things are actually observable to the naked eye. So we would need to use a pH indicator to help us to visualize that. We could also, usually acid-base reactions involve some kind of heat change. So we can monitor the temperature and notice that the temperature is changing in those cases as well. Gas evolution reactions, it's exactly what it sounds like. I put those two things together and a gas forms. So just looking at each of those subclasses, with acid-base reactions, we're putting an acid and a base together. The precipitate, if you will, the thing that tells us that the reaction is happening is the formation of water here. Water is different from what was there present before. Water is formed out of the hydrogen ions and the hydroxide ions reacting with each other to give us this water. Now, again, visually speaking, we don't see anything there from a visual standpoint. But we do see, again, if we use a pH indicator or some other kind of means, there would be ways to monitoring those other kinds of changes. This table from your textbook is a list out of some of the more common acids and bases. So a number of these are things that we have encountered already or countered before. Things like hydrochloric acid, nitric acid, sulfuric acid. Those are all common lab acids that we've had in different ways this semester. Same thing with sodium hydroxide, probably the most common lab base that we have. Some of these other ones have other common uses. Lithium hydroxide is found in lithium ion batteries. Potassium hydroxide is known as potash. Calcium hydroxide is in lime. Acetic acid is the primary active ingredient in vinegar. So when we say they're common, they're common. With the gas evolving reactions, again, double displacement reactions, but we get a gas product as a result. Now that gas product that forms doesn't usually show up in the double displacement reaction as a gas. What it shows up is as an intermediate product, an intermediate acid or base, and that acid or base decomposes into the gas that we're looking for. These are the kind of ones that we usually smell before we see. So, for example, if H2S comes out as a product, we smell that right away. That's rotten egg smell. If sulfurous acid is a byproduct, that sulfurous acid will break down into water and sulfur dioxide. Sulfur dioxide is the odor that you would associate with things like burning tires, burning hair, burning rubber, that kind of thing. That's the sulfur product. Ammonium hydroxide breaks down into ammonia gas. Ammonia gas smells like clean. Carbon dioxide does not have an odor, but we usually know that particular observation. This is that vigorous bubbling that you associate with like a volcano, baking soda vinegar kind of reaction. It's very vigorous. The bubbles themselves have no color, but they bubble up very, very, very fast. I'll skip the piece about redox reactions just to do the kind of end result here. The last class of reactions are combustion reactions. Combustion reactions are when we burn things. Now, in particular, the burning reactions we are talking about most often are burning of hydrocarbons. That is organic or alcoholic kinds of things where carbon, hydrogen, and oxygen are the primary components of that compound. When that happens, water and carbon dioxide are the products of those reactions. Other thing that we characterize about combustion reactions, they're very exothermic. They generate a lot of heat. They usually generate a decent bit of light as well. And we can kind of point to that right away as something to recognize and be aware of. So that's it for today.